Good morning, students. So in the
Good
last,
morning, sir.
Good morning,
good
sir.
morning. Yes,
Good
so
morning, sir.
yes, okay. So in the last class we have started the fluid dynamics. Today we should continue, that is the fluid dynamics. Is it visible?
Yes, sir.
Yes, sir, visible.
So see, at the time of the conservation equations we have discussed, that is the three-dimensional, that is the conservation equations. Here that is the momentum equations when a force or jet is striking some the a stationary or moving body. In that situation, that is the, so here from the Newton's second law, that is the change per unit time in momentum of a body is equal to the force acting on a body. So mv2 minus mv in equal to the ft or divided by 2. So this is the law of the conservation of the momentum. So whenever the reaction force of a jet or the force acting on a solid wall in contact with the flow is to be the obtained. So by using the change in momentum, such a force can be obtained comparatively simple without examining the complex internal field. So in actually keeping, that is the, so here we have shown that is the momentum due to the force acting on a body or wall. Here for C, this is the our two-dimensional, that is the body is shown of a fluid element here A, B, C, D, and a pressure, that is the flow takes place or pressure acting on, that is the our surface AB is P1. It's having the velocity component with x-axis alpha, that is the V1. Here when that is the fluid passes through this curve, that is the, then some force is acting. This resultant force is here given F. It's having two component, Fx, Fy. Similarly the pressure force acting on the other end, which is also making an angle alpha 2 with the velocity v2. So velocity is the outward. So all these are, that is the here written ABCD control, that is the V1 velocity, P1 is the pressure, and F is the force of the fluid acting on the pipe. So the force of the pipe acting on the fluid reaction. So this force and pressures acting on the section AB and CD respectively. So further let F be the force of the fluid, so CD. So then increase in the fluid momentum or increase in the momentum equal to the momentum outgoing minus momentum incoming, or that is the influx of momentum. Is it correct? So Fx by the component of the forces acting speedily. So let us see. Here the forces left side, right side is, that is the momentum. So see Fx, I think so, that is the for here minus Fx plus A1 P1. A1 P1. So pressure force at the section AB, and it is the incline, that is the velocity. So cos alpha 1 minus A2 P2, cos alpha 2 equal to the, that is the mass into V2 cos alpha 2. V2 cos alpha 2 minus V1 cos alpha. Similarly, in the y direction written minus Fy plus A1 P1 sin alpha 1 minus A2 P2 sin alpha 2 equal to the M. Mass of the fluid that is the remains same. Velocity b to due to the changing in the cross-sectional area. That's why it is the giving these reactions. So m v2 sine alpha minus v1 sine alpha. So these are the result. So in this equations is the mass flow rate, and if q is the volumetric flow rate, then mass here is replaced, that is in the term of that is our density, area and velocity, and that will come out that is the discharge form, that is the remains same because cross section is that is the control volume remains that is the same. So q that will come out rho into q. So mass is replaced by the rho into q and rearranging, and that will give you that is the higher equations form the where change the momentum equal to the force, but this since is refer to the mass per unit times, note the equation shows that the time sequence change in momentum is equal to the force. This is the resultant force. So see, these are the general that is the reactions and that is the forces of the change of the momentum or linear momentum. How we should apply these, because you have to also study in sixth semester that is the fluid mechanics. There you can use that is the turbine pump where these are the jet is striking. So let us see a jet. Application of the linear momentum that is here see. So a two dimension that is the here jet is that is the striking on a plate, that is the here as you can see inclined flat plate rest, and it will that is the resolve into the two parts. So the internal pressure of the jet flow is equal to the external one, and that no loss arises from the flow striking the flat plate, and no loss. So it assumes that the fluid flow at the out at the velocity v along flat plate. So the control volume of the figure is here marked. So the direction at the right angle to the flat plate, so velocity, so resultant that is the force is F rho q v sine theta. V sine theta, and its component is along x-axis, and y that is the here written fx is equal to the rho q v sine square theta and f cos theta, that give you the. So then the flow rate along the flat plate separates into q1 and q2. Here it is the given, and the ratio to according to the inclination angle. So flow loss this that is regarded, then it will come out that is the applying equation of the momentum is rho q v cos theta total, that is rho q1 v minus rho q2 v and q cos theta q1 minus q2, where q1 is the q1 plus cos theta q1 minus 2. And since the relate, so in case of where the flat plate moves, this here we have decided the first situation, the flat plate on which that is the jet is striking, that was the fixed. So right now it is moving a jet flow with velocity that is u related to the jet. So flow flat plate v minus u, and flow rate is the q dash reaching the flat plate, since the change in velocity in the direction at right angle to the flat plate is this. So that will come out that is rho q v minus u whole square by v into the sine theta. This is the generalized case. Sometimes we will use the horizontal, vertical, accordingly we can change. So this is about that is the linear momentum striking of a fluid on that is the jet striking on fixed plate, moving plate, then moments of the momentum or angular momentum, moments of inertia into the angular velocity, and torque change in the angular velocity, momentum of inertia into angular acceleration. Here the velocity resolve similar, that is the pattern what we did linear momentum, but this is the rotational. We can resolve it. T, that is the torque or moment acting on that is the plate, and this will give the relations. Right? Another, this is the turbine, that is the your air. So fluid flow rate mass at along the blade due to the rotation of the pump impeller. So see, this is the impeller of the centrifugal pump. Here it is the given, and its moment acting on the our shaft, that is the arm R2 V2 cos alpha 2 minus R1 V1 cos alpha 1. And these things you have to read in the sixth semester when it's fluid machinery and power T into omega. So this is the some theory regarding the momentum equations, angular, linear. Let us come on that is the, again our generalized fluid mechanism, that is the treated as a fluid, a solid body. So here free body diagram of a fluid, that is the Cartesian fluid element is shown here, and the resultant forces are acting here, that is the also giving in the figure weight, that is the here V, that is the volume into J, that is acting downward, our axis is the upward, pressure force and shear stresses force, that is the acting from the Taylor series. Right side is the given P minus T tau xx plus del y del x P minus tau xx dx, and area, and here similarly the this is the normal, or can see that is the given the stresses. And so see here, so mass into acceleration, inertia force, weight of the body. So mass into acceleration plus summation of forces. There are two types of the forces. One is the body force due to its mass, and another one is the surface force due to the viscous system. Due to the viscosity of the fluid, and that will come net surface force in along the x direction is here written, pressure gradient and shear stress into the volume here written. So per unit volume, that is the mass is replaced by the density into volume. So mass, so that is the body force plus surface force, and acceleration is equal to the total derivative of the velocity equal to the local acceleration plus that is the convective acceleration. So body force, that is the rho g, surface force. So surface force due to the pressure, and surface force due to the viscous stresses. These are the forces acting. So here let us see rho. So this term rho into dv by dt here, rho into a equal to the fv plus fs. It is the per unit volume, just why it is written the a small body force, a small surface force. And this here rho into acceleration, that is the total, that is the material derivative dv by dt equal to the body force plus pressure force plus viscous force. See, here that is the surface press viscous force is taken here taken, it should be eliminated due to it is in a stationary position. The fluid element is in a stationary, but it is the air fluid element is taken due to the viscous stress. There is a no such type of the viscous. Then the inertia force, body force due to gravity, surface force due to the pressure gradient. So this that you should take in the regularized when it is the that is the zero that will come out. So pressure, so rigid body translation and rotations. In rigid body all particles are in combined, either that is the translation and rotations, no relative motion between the fluid particle. So there are no strains and no its deformation. So from the Navier-Stokes equations, it is that is rho into A. Rho into A equal to the minus del that is the pressure gradient plus rho into G, and that is the viscous term mu into del square V equal to 0. This is the rearranging written in the del P equal to the rho G minus rho A, from which that is this so direction that is the acting, and G minus A. Right? So from which the C that is the del PG, and line of constant pressure must be perpendicular to this direction. See, the rigid body of fluid translating and rotating, that is the air point with respect to the origin O, rotation that is the omega, that is the air ohm, that is the given particle P with acceleration A. So the generalized that is the translation rotation, if center of rotation that is the V equal to the V0 into omega plus R0, and angular velocity vector and acceleration equal to the V. So acceleration equal to the dv by dt. So dv0 that is the initial velocity of the our rigid fluid element plus omega into omega cross omega r plus d omega by dt plus rr is the position vector. So acceleration one that is the acceleration of the our body center. Two that is the centripetal acceleration of the fluid particle relative to the O. Three is the linear acceleration. So uniform linear acceleration case, let us see. This is the a fluid moving, that is the linear acceleration, that is the air fluid that is the taken air. So acceleration that is a two-dimensional, it is the written axi plus ay z here, it is the written. So del P pressure gradient rho G from the Navier-Stokes equation, and that is the dissipation term is eliminated, that is the mu del square V is constant, and this minus rho G plus AZ. So see, this is the acceleration, it is the given here acceleration and generalized for an unit vector in the direction. So that's theta of that is the here given of the your resultant tan theta equal to the acceleration along x-axis divided by the g plus a, and dpy dx that is the rho x g a z square. Then rigid body in rotations. So del P equal to the again that is the same equations rho G minus A, and we are rotating with the omega of that, then the profile of the fluid uh, after the rotation will become the parabolic, and different that is the forces that is the acting on the fluid element is shown. So water level, when it is the in a dotted stream, that is the level. After rotation it will become that is the solid line in a curve, which is the parabolic form. So acceleration, that is the rotation omega into omega dot r0, and pressure gradient from the momentum equations, that is the written. So P equal to the rho I 2 r square omega square minus rho g z constant. So the constant is determined specifying the pressure at one point. So P equal to the P0. This is the initial pressure. Sometimes it may be that is the zero, sometimes it is a specified. So the curve that will form a plus b square revolution, and which are the paraboloid curve constant, that is the given is the a, that is the a plus b square, where a is given. So this is the all about that is the your fluid dynamics regarding the theory. Am I right? So here importance, that is the rotations of the any fluid element in a container that make a profile of the parabolic. Then translation rotation, that is the rho A equal to the minus del P by gamma. So this is the some idea regarding the fluid mechanics, fluid dynamics. Let us we will take some examples. Just wait. Then you can give the idea. Yes, please write down. Hello, are you listening or
Yes,
not
sir.
listening? Please write down a problem. A vertical tank resting on a smooth rollers. A vertical tank resting on a smooth rollers have a circular orifice. A vertical tank resting on a smooth rollers have a circular orifice 25 mm diameter. 25 mm diameter in its vertical side. in its vertical side. It discharges 1.45 kg per second of water. It discharges 1.45 kg per second of water through the orifice. 1.45 kg of the water through the orifice. When the depth of the water when the depth of the water in the tank is 1.2 meter. When the depth of the water in the tank is 1.2 meter above the center line of the orifice. 1.2 meter above the center line of the orifice. Full stop. At this condition, at this condition, a horizontal force of 7 Newton, a horizontal force of 7 Newton in line with the center line of the orifice, a horizontal force of 7 Newton in line with the center line of the orifice is required to keep the tank at rest. To keep the tank at rest. Full stop. Find coefficient of discharge, velocity, and contraction. All three coefficients you have to find out. Have you written the question or not? Tell me, have you written or not? Please confirm again, I am going to read it. A vertical tank resting on a smooth rollers have a circular orifice 25 mm diameter in its vertical side. It discharges 1.45 kg per second of water through the orifice when the depth of water in the tank is 1.2 meter above the center line of the orifice. At these conditions, a horizontal force of 7 Newton in line with the center line of the orifice is required to keep the tank at rest. Full stop. Find coefficients of discharge, velocity, and contraction. All of you please try it in this mean period. I will call the attendance. Attention please, response your roll call. And you continue try to solve the problem. After the attendance, I will give the solution. Roll number 1, 2, 3, 4,
Present, sir.
5, 6, 7,
Present, sir, 7.
Okay. 8,
Present, sir.
9, 10, 11, 12, 13,
Present, sir.
14,
Present, sir.
15,
Present, sir.
16,
Present, sir.
17, 18,
Present, sir.
19, 20,
Present, sir.
21,
Present, sir.
22,
Present,
20,
sir.
23,
Present, sir.
24,
Present, sir.
25,
Present, sir.
26,
Present, sir.
27, 28,
Present, sir.
29,
Present, sir.
30, 31,
Present, sir.
32,
Present, sir.
33,
Present, sir.
34,
Present, sir.
35,
Present, sir.
36.
Present, sir.
So see, here that is the given. It correct. So first find out the theoretical velocity. So V theoretical equal to the root under 2gh. We have already discussed the theory of that is the orifice. So what that is the theoretical velocity equal to the root under 2gh. What is the h? H is the given here. See, it is the given. The depth of the water in the tank is 1.2 meter above the center line of the orifice, above the center line. This is the due to this height, this velocity that coming out theoretically. So theoretical velocity equal to the root under 2gh, 2 into 9.81 into 1.2. How much come out? Tell me. कितना आया बोलिए v theoretical. Just tell me v theoretical how much you got it. Root under 2 into 9.81 into 1.2, that will come out 4.852 meter per second. Is it correct or not?
Yes, sir.
Then Q theoretical, discharge theoretical, area into theoretical velocity, and diameter is given. Diameter is 25 millimeter. So pi by 4 d square into v theoretical. So pi by 4 into 0.025 whole square plus 4.852. That will discharge is come out 2.38 into 10 to power minus 3 meter cube per second. All of you got it or not? So up to here we have completed Q theoretical. Then continue the attendance. Roll number 37, 38, 39,
Present,
40,
sir. Sir,
39.
39 present.
Okay,
Yes,
okay,
sir.
okay. 40, 41,
40 present, sir.
okay. 41, 42,
Present, sir.
43,
Present, sir.
44, 45,
Present, sir.
46, 47, 48,
Present, sir.
49,
Present, sir.
50, 51,
Present, sir.
52, 53,
Present, sir.
54,
Present, sir.
55,
Present, sir.
56,
Present, sir.
57, 58, 59, 60, 61.
60 present.
Yes, sir. Present, sir.
Okay,
61 present.
okay. 62, 63,
Present, sir.
64, 65,
Present, sir.
66, 67,
Present, sir. 66.
67, 68,
Present, sir.
69,
69 present, sir.
okay, 70, 71,
70 present, sir.
70%, 71, 72.
Present, sir.
So yes, continue the problem. So let us Q theoretical we have discussed that is the we got 2.38 into 10 to power minus 3 meter cube per second. What is the actual discharge? So it is a given or not given. What is the actual discharge? Tell me. So here it discharges 1.45 kg of water. This is the actual discharge is given. So see here that is the given. So kg per second, that is the, so see then, so here that is the 1.45 divided by the density of the water. So taking 1000, that will come out the discharge. Density equal to the mass divided by the volume, or volume, that will come out velocity. So that is the velocity mass, the rate of mass into density. So actual discharge is 1.45 divided by the density of water, 1000, let us say. So actual discharge is 1.45 into 10 to power 3 meter cube per second. Discharge is given, but it is given mass per, that is the rate, mass rate, kg per second. We have to transfer, that is the in volume per second. So density we should multiply, that will come out. So we got Q theoretical, Q actual. Then find out the CD, coefficient of discharge. So coefficient of discharge equal to the actual discharge divided by the theoretical discharge. And actual discharge is 1.45 into 10 to power minus 3 divided by the theoretical discharge. We got 2.38 into 10 to power minus 3. And so coefficient of discharge will come out 0.6092. 0.6092 means 0.61. So we got the coefficient of discharge only, and you have to still find out coefficient of velocity and coefficient of contraction. So see from here, that is the given the horizontal force, so that sustaining the tank in that is that position. So the force required to arrest the backward reactive movement of the tank is the rate of change of momentum of the liquid. So F equal to the m dot v, and it is the rest. Second velocity is 0, so change of the, so F equal to the m dot v. F is given, that is the 7 Newton is given, and mass rate is given. So F equal to the mass into velocity divided by the time, and that time will become rate of mass m dot, and which is a given. So velocity that will come out, that is the 4 point. So Fym dot. So that is the 7 divided by 1.45. So V velocity will come out, that is the 4.827 meter per second. And C, we got that is the actual velocity 4.827 meter per second. And theoretical we have already calculated, that is the 4.852. So coefficient of velocity equal to the actual velocity divided by the theoretical velocity, and actual velocity just we have calculated from the momentum equations. 4.827 divided by 4.85. So coefficient of velocity will come out 0.995. And simply you have to find out coefficient of contraction. Continue the attendance. Roll number 73, 74,
74 present, sir.
75,
73 present.
76,
76 present, sir.
77,
Present, sir.
78, 79,
Present, sir.
80,
Yes, sir.
81, 82, 83, 84,
Present, sir. 81 present, sir. Mic not working. 84 also present.
85,
Present, sir.
86,
What is it now?
87,
87 present, sir.
88,
Present, sir.
89,
Yes, sir. 89 present.
90,
90%, sir.
91,
Present, sir. 91.
92,
Present, sir.
93,
Present, sir.
94, 94, 95,
Present,
90,
sir.
95,
Yes, sir. 95 present.
96, 97, 98, 99,
Present, sir. 99.
100, 101,
Yes, sir. Sir, 100 present.
okay,
Present,
100,
sir.
102,
Present, sir.
103,
Present, sir.
104,
Yes, sir.
Present, sir. Present, sir. Present, sir. Present, sir.
105,
Yes, sir.
106, 107,
Present, sir.
108.
Present, sir.
Rest. So just tell me, what is the coefficient of contraction? We got the coefficient of discharge 0.61 or 0.6092. Coefficient of velocity is 0.995. Then what is the coefficient of contraction? What is the relations? Coefficient of discharge equal to the coefficient of velocity into the coefficient of contraction. CD equal to the CB into the CC. So in this way, we can calculate the coefficient of contraction, and it is nothing but the product of 0.6092 into the 0.995. Yes, please write down another problem. A converging pipe is 20 centimeter inlet. A converging pipe is 20 centimeter inlet and 10 centimeter outlet. 10 centimeter outlet and 5 meter long. 5 meter long is lying in the vertical plane. 5 meter long is lying in the vertical plane, making an angle 45 degree to the horizontal. Means this pipe is making 45 degree with the x-axis to the horizontal, and the pipe is carrying the water. The pipe is carrying the water 24 meter cube per minute. The pipe is carrying the water 24 meter cube per minute. Full stop. The pressure of the water at the inlet, the pressure of the water at the inlet is 500 kilopascal. The pressure of the water at the inlet is 500 kilopascal. Find the pressure of the water at the exit. Find the pressure of the water at the exit. Yes, please try to complete it. Yes, attendance come continue. 109.
Present, sir.
So after that is the 109, 110.
109 present, sir.
Okay, 110, 111,
Present, sir.
112,
Present, sir.
113,
Present, sir.
114,
Yes, sir.
115,
Present, sir.
116,
Present, sir.
117,
Present, sir.
118,
Present, sir.
119,
Present, sir.
120,
Present, sir.
121,
Present, sir.
122.
Present, sir.
Any more? और इसमें और आगे नहीं ना है नेक्स्ट?
Sir, 98, sir.
Sir, 27, sir. Roll 3. Sir, 27.
So
Sir,
only
3.
roll number 109 to 122. Anybody have? No. Okay, just wait. So see, first we will complete the problem. So see, so our converging, that is the diverging, that is the inlet outlet pipe. So bottom side is the dia is 20 centimeter and exit side out, that is the top is the 10 centimeter, and it is 5 meter long, and it may, that is the incline to the horizontal with 45 degree, and that is the discharge Q is given 24 meter cube per minute. Inlet pressure is given 500 kilopascal. Then tell me that is the pressure at the exit. Tell me the pressure at the exit. कितना यस कितना आया बोलिए आप लोग को. Attention please. Roll number 1, 2, 3. कितना?
Sir, roll number 2, sir.
कितना?
Roll 2.
2, 3,
Present, sir.
5, 6,
Present, sir. Roll number 6, present, sir.
9, 10, 11.
Present, sir.
कितना? 11,
11. Yes, sir.
12, 17, 19, 27,
Yes, sir, 27.
30, 37.
Present, sir. 37.
लास्ट क्लास में प्रेजेंट था 37 और एब्सेंट था 37.
Yes, sir. Present, sir.
आर यू श्योर कि नहीं पता है
Yes.
तुमको?
Yes, sir. Yes, sir.
38.
Present, sir. 38 present.
Okay, 41, 44, 46, 47, 50, 52. These are, that is, they are existing or not? ये सब रोल नंबर एग्जिस्ट कर रहा है कि नहीं? स्टूडेंट्स आर Enroll or not enroll?
Enroll, sir.
Acha, okay. Roll number 57,
Present, sir.
58, 59, 62, 64, 67, 71, 71, 73,
Present, sir.
73. लास्ट क्लास था, yes or not?
No, sir. सर शादी पड़ा था सर, शादी में चले
Okay,
गए थे
thank
सर.
you. Okay, thank you. Honestly, आपने बोला था, it is thank you. Okay. 74.
Present, sir.
Oh, you 78. Sorry, 78, 82, 83, 86, 96, 97, 98.
Present, sir. 98.
Okay. लास्ट क्लास था कि नहीं?
हाँ सर.
106, 110. So see, so that pressure at the exit that will come out, that is the here first, that is the apply, that is the Bernoulli equations at the point 1 and 2, and then pressure will be come out 2.593 bar. That's all. So this is the all about, that is the today class. Tomorrow we will also take, that is the example of, that is the fluid dynamics. Am I right? And today I am going to send the notes. So you go through this one and discuss, that is the any query, then ask me please. If you have
No,
any
sir.
query. Okay, thank you.
Thank you, sir.
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 Yes, sir.